more the subject of chapter 22. What we've been doing here is chapter 21. I've got the new homework problems posted. They're not due on Tuesday. You won't be tested on the electrostatic stuff on Tuesday. But there'll be another quiz 2 weeks from Tuesday that'll just have this stuff on it. And then the midterm is going to be heavily weighted on this stuff. Next midterm. I know sometimes the concept of an electric field is confusing. You can say, well, why do these two charges have an effect on each other? Here's, say, let's call this Q naught. That's kind of what it is. Or divided by, okay, so that's Q naught. So we can make this big Q and this Q naught. And let's say that they're repulsive, meaning that they're equal in magnitude, or they're both positive or negative charges. Okay, so we might ask then, it's a logical question to ask, how could that possibly happen? How could you have two objects that aren't in physical contact exerting a force on each other? I could certainly explain the fact that I can exert a force on this table if I'm in direct contact with it and I'm pushing it, okay? Because I'm right there pushing on it. But how on Earth or how in the universe can two objects that aren't in physical contact have an effect on each other? What is it that's making that happen? And it's similar to the same question that Newton asked about why does gravity work? Why is it an inverse square law? And how do two objects that aren't in physical contact attract toward each other in the law of gravitation? It's a similar question. Those are called distance forces. And it's something that we'll get into a lot more detail about the physical mechanisms for distance forces in Physics 2.8c. But it's pretty weird stuff. You can actually think of these particles as throwing little virtual particles at each other. They catch those virtual particles and then they recoil. Okay? But another way of thinking of this is just in terms of there must be a disturbance in the space. Because if this charge weren't there, there'd be no force. But then we put that charge there, now there's a force. So there must be something about the property of the space right here that is being altered by Q. And we call that property of the space the electric field. So this is some kind of a distortion of the space, because if that charge weren't there, then there wouldn't be a force at that point in the space. So there must be something about this charge that's altering the space at this location. And we call that the electric field. So that's just a property of the space around the charge Q that is produced by the charge. So we call that the electric field. We give it a symbol E. Okay, so before we can make more sense out of that, we need to know what a field is. And so there's two different types of fields. A scalar field and a vector field. would be, say, temperature. You have a numerical value for a physical quantity at every point in the space. And so, in other words, at every point in this room, I can go around with the thermometer and I can measure the numerical value for the temperature in the room. That I wouldn't refer to the trash can field because this is a localized object. This does not contain a numerical value at every point in the space, but temperature does. I can go around, I can measure the temperature, and so there's a value for the temperature. And so that's how we define a scalar field. Now it doesn't have a direction if it's a scalar field, but a vector field has a magnitude and a direction at every point in the space. Okay, and so an example of this then would be wind velocity. Now, you're not going to have a lot of wind in this room, but if you go onto your weather app, a lot of times it'll give you the direction of the wind and the magnitude of the wind. Okay, and so let's say the wind is blowing this way, so that's the direction. In meteorology, a lot of times they talk about what it's coming from. Okay, so this would be, even though it's pointed toward the east, we call it a westerly wind because it's coming from the west. Okay, that's not important for this class, but that's just the terminology. And so this would be a westerly wind at 15 miles per hour. Pretty stiff breeze. Okay, so that would be a vector quantity, but I could go around to every single point. And in this room too, even though there might just be a little fan going, there could be small variations in the wind velocity from point to point in this room. So that would be a vector field. Okay, so the electric field is a special kind of vector field. And you can imagine it in terms of these electric field lines. Okay, so if it's a positive value, then at this point P, there's going to be a certain electric field vector that'll point straight away from positive, but for this negative charge, the electric field will point straight toward negative from a particular point. So these electric field lines then give you an opportunity to see what the symmetry is of these electric fields. And so they emanate in much the same way as light rays would away from a light source. So although it's much more abstract than that, you can imagine it to be like a light bulb that's shining out light rays. So we already know how those should look. So you can imagine that this positive charge is shining, quote, shining out electric fields. And these electric fields don't move instantaneously fast. The presence of a charge can produce electric fields, but they can only move at the speed of light. So you're not going to know about an electric field or a gravitational field changed until that source has had a chance to get to you. So for example, with the sun. if a black hole came through our solar system right now and took out our sun, it wouldn't immediately take out the gravitational field here at the Earth. It would take 8 minutes for us to realize that something horrible had happened. So we'd be looking, and we'd see the light from the sun still shining. We wouldn't feel any difference in the gravity force, even though our sun is gone. We wouldn't know about it for 8 minutes and 20 seconds, which is how long it would take the light to travel 93 million miles. Okay, and so this is a similar kind of thing. We have gravitational fields that extend out in a spherically symmetric fashion away from masses. We have electric fields that extend out. And so this is just a way of measuring the disturbance in the space that is produced by the charge. And so when you try to get down deeper than that, say, what is it really? Well, then you have to describe it in terms of other things. And the problem is, these are fundamental. So how do you describe something that's fundamental in terms of other things? So that's a problem in getting a real clear grasp of what the true nature of an electric field is. But it's very basic to our existence. But we can still say it's like other things that we're familiar with, like light rays. And then that can give us something that we can connect to. I've had PhDs in chemistry. The college me, I never understood the electric field. So it's not, but if you can work with it, maybe nobody fully understands it deep down, but we can still work with it, and it's a very useful tool. So here's our charge big Q. And so here, if we had some charge little q, Q naught, there'd be a force on it. So we define the electric field E as being the force on the charge divided by the charge. So in other words, it's what the force would have been on the charge if the charge had been there, but the charge isn't there. So it's the force without the charge. You want to think of it that way. Or force per unit charge. But we don't want to be confused into thinking that the electric field is a force. And that's something that's really easy to do, especially because I just finished spending an hour working out electric forces. And so what people are going to want to do then is, when I ask for an electric field, they're going to want to find the force between the charged particles. And I don't know how to avoid that, because if I start out with electric fields, that's just too abstract a way to start. But if I start out with the forces between charges, then everybody mixes up the electric field with the force. So I'm just throwing that out there so that maybe that won't happen to you. All right, so this is our electric field pattern. At each point in the space, we have a different value for the electric field. And so here it would have this length, but out here it would be smaller. So this would be E1, this would be E2. So how can we figure those out? Well, we could say that E is equal to the force, K, big Q, Q naught over R squared, divided by Q naught. Okay, so that's the force at this point. That's F1. Divided by Q naught. So E1 is F1 over Q naught. E2 is F2 over Q naught. But instead of writing it that way every single time, let's just simplify this and cancel out the Q naughts. So then we just have something that looks like K, Q. So this only involves the charge that's producing the electric field at this point. divided by r squared. And we'll write this times some unit vector that points in the spherical coordinates r hat direction. So the spherical coordinates r hat is different from the cylindrical coordinates r hat. R hat in cylindrical coordinates points straight away from the cylinder that has an axis z. But for a sphere, the r hat points straight away from the sphere. In every direction, it points straight away. And here, this would be r hat down there. Here, r hat, r hat, r hat. Spherically away from the center of the sphere. Okay, so given that, let's figure out the electric field at the midpoint between two equal charges that are opposite in sign. So this is Q, this is minus Q. Then let's make this distance 2L equals, let's say, 2 meters. So the magnitude of Q equals 10 to the minus 5 coulombs. Let's find the electric field at the midpoint. Between the two charges. Okay, well we can, if I call this charge 1, then I'm going to have an E1. Remember, the electric field points away from positive and toward negative. It's away from positive and toward negative. So this would be my E1. And then for charge 2, it points toward negative, so that's in the same direction. So the two are going to add. Okay, so this is not the force between the two charges. This is what people get mixed up on. Not the force between the two charges. It is the effect on the space produced by these two charges at another location. So why is that useful? Well, because now, once I know what the electric field is, I can put another charge there, and I can figure out the force. So that's the utility of this. That's why we're going through all of this. Of course, there mathematically are many other super important reasons for doing this too. But the utility of E is once we know E, then we can find the force. And that's just going to equal Q naught times E. So once we put a charge at that location, then we have a force. But we don't have a force until there's a charge there. We just have a disturbance in the space that's been produced by those two charges at that location.
Can you explain how E appeared?
How what?
You had E1 and then
Well, that was just some generic E. And so in this case, you've got an electric field due to charge 1 and due to charge 2. So E total is going to be a vector because it's a vector field, so that'll be E1 plus E2. So E1 and E2 are in the same direction, so we don't have to worry about components adding or canceling. That's just E1, E2. So that's what we're going to have there. That's going to be our total electric field at that midpoint. So this is the utility of this then. It's not meant to be confusing. I know that it can be, but it's not meant to be that way. It's supposed to actually make things better, because in some situations you have very complicated charge configurations. And so it's easier, instead of figuring out the forces between an infinite number of charges, it's easier to figure out the electric field due to the charge configuration, and then just put a charge there, and then find the force on it. And so that's why the electric field is considered to be, in some respects, a more fundamental quantity than the force. Any other questions so far? So this concept's important, yeah.
Is this Newton's work as well, or is this beyond him?
Yeah, Newton didn't go this far. Yeah, this stuff was figured out more in the 1800s. And then Maxwell is the one that united electricity and magnetism and found out that interactions between the two produce light. And so it's a mutual interaction between electric fields and magnetic fields that kind of invents a light ray as it moves along. So he's able to, Maxwell, that was around 1860 or so, figured out that the speed of light was actually this interaction that he could calculate between the electric and magnetic fields. And at that point, they'd been able to measure the speed of light, so they verified that all that stuff was working. All right, so let's do a numerical calculation with this. If we know what the charge is, and we know what the distance is, let's find the total electric field at the midpoint. So that's going to be E1 plus E2. How do I know to add them? Because I see here that from my rules, I'm pointing away from positive for E1, but I'm pointing toward negative for E2. And so that means that in terms of my coordinate system, they're both adding together. And so this is just going to be K Q over L squared plus K Q over L squared. It's just this charge at this distance away. So no Q squareds in here anymore. Not a force. This is just the electric field here. Then I can put a charge there and get a force. So that just gives me 2 KQ over L squared. So for this problem, and that would be times some unit vector that points in the plus I hat direction. This would be I hat, J hat. And so plug in the numbers, you get 2 times 9, 10 to the 9 Newton meters squared per Coulomb squared times 10 to the minus 5 coulombs. That was the charge divided by, and I made this distance 2L equal to 2 meters, so that L equals 1 meter. That just makes my numbers come out easier. That's going to be divided by 1 squared. So that's what we've got here. So that's going to be 2 times 9 is 18 times 10 to the minus 1. I'm sorry, 10 to the minus 10 to the 5. Sorry. 9 minus 5 is 4. 10 to the 4. Oops. So that's going to be 1.8 times 10 to the 5 something. So what is that something? Well, it's going to have units of force divided by charge. So that would be Newton per Coulomb. So that's the way we write the electric field, is as a certain number of newtons per coulomb. And it turns out there's also an equivalent set of units that we'll see later called volts per meter. That's the same thing as units per coulomb. But for the moment, we don't know what volts are, so we don't have to worry about that. So it's just that. And so that's the electric field. So it's about, what's that, 180,000 newtons per coulomb. Now let's, just to see what the utility of this is, remember we said this isn't really that important unless we put some charge there. So this is kind of a picture of what I did, you see, right in the middle there. So the extension of this field line at this point gives us an E1. The extension of this that's pointing toward negative at that location gives me my E2. But now let's put a big charge there, big Q. So let's put big Q equals 2 times 10 to the minus 5 coulombs. Place it at this point. Then you're going to have a force, F, that's equal to Q times E. Because remember, electric field was force per unit charge. So therefore, and you can see the units, newtons per coulomb times coulombs is newtons. Okay, so this is kind of the equivalent of F equals ma with gravitational problems. F equals mg if you're doing a gravity problem. But here, if you know the electric field, then you just have to multiply it by the charge, and it's so easy at that point. You've done all the dirty work by figuring out what the electric field was over here. Then all you have to do is put a charge there at that point, and then that charge is going to experience a force due to each one, and that force is just going to be QE. So for this problem, that would be 2 times 10 to the minus 5 coulombs times 1.8 times 10 to the plus 5 newtons per coulomb. The 10 to the 5 and the 10 to the minus 5 cancel, or they give us 10 to the 0, which is 1. So we get 2 times 1.8 is 3.6 newtons. So this is another alternative way to do the problem. So you say, well, why do it two different ways? I could have just figured out the force here and the force there from the beginning, and then I didn't have to worry about the electric field, which was confusing me anyway. And so that would be a valid argument if that's the only reason why we ever used it. That, as I mentioned before, if you have a continuous distribution of charge, it's more convenient to find the little bits of electric field due to each little bit of charge, add them together as an integral to get the total electric field. Then once you've done that, you can then take a charge and put it at that location, and you've got a much simpler problem to solve than an infinite sum of different forces. So it's easier to work with because we're going to be dealing with more complicated charge distributions as time goes on. Okay, so that's the intro to electric field. Next time before our quiz, I'll do some more with examples of electric field. But for the moment, we have that in-class activity. Let me just point a couple of things out to you about it.